Okay, so it says farmer wants to fence an area of, wow, 1.5 million square feet in a rectangular field and then divide it in half with a fence parallel to, yeah, there should be one in the middle drawer there. No? So on the left, top left, you'll probably have to open a new box. Um, and then divide it in half with a fence parallel to one of the sides of the rectangle. How can he do this so as to minimize the cost of the fence? So the cost of the fence is going to be based on the what? The perimeter, right. So what we're trying to minimize is the perimeter. So that's the equation that we're going to end up taking the derivative of. But before we do that, let's label some sides. X and Y. It's not going to be an x cubed and a y squared for the perimeter because perimeter is adding, not multiplying. So the perimeter is going to equal 3x's plus 2y's, yeah. And then we would like to take the derivative of that and set it equal to 0, but there's two variables in there. So what is a relationship we can find between the two? Okay, we know the area is 1.5 million, so x times y is equal to 1.5. Then we got to solve for either x or y. Which one? X. Sorry, I just barely heard him first. It's closer. Sound travels, you know. X over 1.5 equals y. So now we can write the perimeter as 3 times 1.5 over y plus 2y, which simplifies to 4.5y to the negative 1 plus 2y. How do we do so far? You all right about that? Because 3 times 1.5 is 4.5, and I can get this y to the first power on the bottom up to the top by making it a y to the negative 1. Okay, yeah, so now that we have and understand that, I can take the derivative of that. So what's the derivative of 4.5y to the negative 1? Good. And again, we're going to take that and set it equal to 0. How do you want to solve that? Subtract. Are you sure? Add. Are you sure? No, I'm just like, you just said subtract, like subtract? Like you weren't really sure. We can subtract. So let's go negative 4.5. I'm going to switch this back down to the bottom because I can't really do algebra with negative exponents. I can do derivatives with negative exponents, but I can't really do algebra with negative exponents. So I'm going to make that y squared down there. Subtract 2 from both sides, like Payson said. Now what? But the 4.5 is on the top. So I could multiply by 1 over negative 4.5. But then I would end up with 1 over y squared, not y squared. What's a better step to get rid of? Yeah, let's go ahead and multiply both sides by y squared. Okay? So that means the y squareds over here cancel. And then that gives me negative 2y squared equals negative 4.5. Now what? Yeah, so I could multiply by negative 1 to make them both positive. Yeah. Because I just kind of like having the variables on the left. I just switched it around, but it's the same. I just took this side and put it on that side and that side and put it on that side. Okay, then divide by 2 and take the square root. So y squared equals 2.5. So that means y equals, what is it? 2.25? Oh, no, I divided the, oh yeah, I see what you're saying. So I did that wrong. Ah, okay, so that makes the square root be 1.5. Okay, so then I take the square root of both sides, and that gives me 1.5, yeah. Okay, so if y is 1.5, ooh, this is exciting. What is x? Yeah, 1. Um, that's in millions. Yeah, that's a lot of feet of fence. How could that even be? It is. So where did we? What is this greater than 2.25, 1.5, Maggie? The square root of 2,250,000. Okay. So it's 0.15? No. Huh. Okay, so it's because we're not really taking the square root of 2.25. We're taking the square root of 2.25 million, and that does change it. What's the square root of 2.25 million? Right. 2.25 million. So the square root of that is, right, only, what'd you say, 1,500. Yeah. Because we would have, if we're going to take the square root of 2.25 million, we have to take the square root of the 2.25, which is 1.5. And then we also have to take the square root of the million, which would be 1,000. So it's 1.5 thousand, not 1.5 million. Okay? And then that means that x is equal to 1,000. So say, man, that'd be a long fence. 1.5 million feet. Yeah, I was kind of wondering that too. 1.5 million feet. One point five times 10 to the sixth, because that's 1.5 million, divided by 5,280. 284 mile long fence. Yeah, 284 miles. That's a pretty long fence. Yeah, right. I mean, that's like, wait. No, I don't want to say it. No. Tenino did what? Okay, number 12. A box with a square base and an open top must have a volume of 32,000 cubic centimeters. So here's my box. And we know, let's see, it's a square base, so this is going to be x, and that's also going to be x. And then the height is going to be y. Okay? So find the dimensions of the box that minimize the amount of material used. What would be the amount of material in this case? Right, the surface area. And remember that it's an open top box. What's the area of the bottom? X squared. What's the area of one of the sides? And how many sides are there? 4, because it's got no top. So x squared plus 4xy is the surface area of the box. Again, two variables. Got to solve for one of them. So if we know that the volume is 32,000 cubic centimeters, what's an equation we can write with that? What's the volume? What's the formula for the volume of this box? What? X squared h, we used y, yeah, but x squared, the area of the base times the height. X squared times y. We know that that equals 32,000. All right, Tegan, chance to redeem yourself. What are you going to solve for? Okay, is that what you did too, Elena? Okay. So You solve for h, yeah, okay. So we divide both sides by x squared. So that means y equals 32,000 divided by x squared. So, yep, so I'm going to resubstitute that back into here. So I'm going to go x squared plus 4x times, and then instead of writing y, or h in your case, Elena, I'm going to write 32,000 x to the negative 2. So that's the formula for the surface area of the box using only one variable. Well, we can simplify that, obviously, a little bit. What's 4 times 32? Okay, so that's 128,000. And then what's x times x to the negative 2? What do you do with the exponents? Add them, so x to the negative 1. All right? How do you guys feel about that first part of the problem? Draw a picture, put some variables in there, solve for one, plug it in. Because this was an x squared on the bottom, right? So that made it an x to the negative 2 when I moved it up to the top. And then when I distributed this, x to the first times x to the negative 2 is x to the negative 1, because you just add the exponents when we take the derivative. Yeah. All right, so now let's take the derivative. So what's the derivative of x squared? 2x. And what's the derivative of the other piece? Negative 128,000 x to the negative 2. And I want to take that and set it equal to 0. Okay. How do I solve that? Okay, great idea. We can divide by 2 to make these numbers a little bit easier to work with. So that will give me x minus 64,000. And while I'm at it, I'm going to just put that x squared back on the bottom, because that makes the algebra a little bit easier to do. Okay, what else? Multiply everybody by x squared, so this x squared down here will cancel. So that gives me x cubed minus 64,000 equals 0. Okay, so x cubed equals 64,000. Cube root, and the cube root of 64 is 4, and the cube root of 3 zeros is just 1 0, right? So that means that x is going to equal 40, bless you, centimeters. So if I plug that back in, y, or the height, is okay. Just trying to find the values. Yep, trying to find the dimensions of the box. You've been hired as a product engineer, Payson, and those are your constraints, and they need to know how big to make the box. So like we want it to be square, so it packs easily. We need to hold 32,000 cubic centimeters of stuff. How big should we make it? You do the math, figure out the dimensions, send it back, and then you make the product. And you get paid bank. Yeah. Yeah, I believe it. Okay, number 13. If 1,200 square centimeters of material is available to make a box, so now we're going backwards. Okay, so in this case, they've told us we only want to use this much material, but we want it to hold as much stuff as possible. So now we're going to maximize the volume. What's that? Right, so this time we know the surface area, and conveniently we already know all this stuff from the last problem. Elena, I'm just going to stay consistent and go x and y. Okay, so this time we're trying to find the largest possible volume, so the formula for the volume is x squared times y, area of the base times the height. So now it's going to be a little bit trickier. What was our surface area formula? Okay, x squared plus 4xy, we know that that equals 1200. So now you have to solve for a variable there. Did you? Okay. I'm going to go ahead and go with y because there's only one y and it's not squared or anything, but it's still not going to be very pretty. So I have to subtract x squared first, and then I have to divide by 4x. So those cancel. So y equals, what is 1200 divided by 4? 300. And I'm going to make that Tegan x to the negative 1. I hope that doesn't stress you out. Okay. And then what does this work out to be here? 1/4 x. Good. Well, this has a 1 in front of it, right, that we just don't write. So that's where the 1/4 comes from. And then x squared divided by x, there's 2 x's multiplied on top, 1 on the bottom, 1 each canceled, and you're all set, okay? Okay, so now I have to take that and substitute it back into my volume equation because that's what I'm trying to, in this case, maximize. So I'm going to go, whoops, x squared times 300x to the negative 1 minus 1/4 x. Say again? For the volume? Okay, I will never mind again. And now I'm going to distribute the x squared. So 300x minus, oh, no negative exponents. Okay? Creeping me out, man. Hey, Mason. Alright, so I'm going to derivatize it. So the derivative of the volume is equal to 300 right? And then, yeah, equals 0. You want to subtract 300? So, yeah, I can make these both positive. How do I get rid of the 3/4? Multiply by the reciprocal. Okay, so what do I get there? 400? Yeah? Because, yeah, okay. And so that means x equals 20 again. Is that the same answer as last time? It is? Oh, it's opposite. Okay. So if x equals 20, you did this already, Elena, you plugged this in. If I plug in 20 there, that's going to give me 80. I don't like that very much. 1200 divided by 80 is 120 divided by 8 is 60 divided by 4 is 15. So then 15 minus 1/4 of 20, so I feel like 10. I could be totally wrong though. That was a lot of weird mental math. How hungry are you? Alright, then last one. What time were we out? 40? Okay. Oh, it's another rectangular, this time it's a rectangular storage container. A rectangular storage container with an open top is to have a volume of 10 cubic meters. The length of its base is twice the width. Oh boy, this looks pretty serious. Oh no, material for the base costs $10 per square meter. Material for the sides only costs $6 per square meter. Find the cost of materials for the cheapest such container. So now two things have changed. One is that we no longer have a square base, we have a rectangular base, but there is a relationship between those two sides. It says the length of the base is twice the width, so if that's x, then this is going to be 2x, and then I'm going to just keep bugging Elena and stick with y there, okay? So we are trying to minimize the cost of the materials. How do I figure out how much that's going to cost? What's the area of the base? 2x times x, or 2x squared. How much do the base materials cost? $10 per square meter. So I have to take that area and multiply it by 10. Okay? Plus, what's the area of all the sides? We're going to have some different things going on here, not like last time where they're all the same. So I've got 2xy right here, right? Or were you doing 2xy because of two sides? Oh, okay. So this side is xy, that side is xy, so that gives me 2xy. Plus, how much is the front? 2xy, the height is still y. So then another 2xy in the back, so that's going to be 4xy. What's that? I'm only doing the sides. How much does the material for the sides cost? Only $6 because it doesn't have to be as strong as the base to hold up the stuff. So I can simplify this a little bit. What does that work out to be? 20x squared plus 2xy plus 4xy makes 6xy times the $6 per square meter is 36xy. So that is our cost function. That's a lot. That's a lot of thinking. What? Okay, now we have to figure out, yeah, we got to get a relationship between the x and the y. What do we know about the volume of the box? It's 10 cubic meters, and what's the formula for the volume of the box? Good, 2x squared y, and that has to equal 10 cubic meters. So what are we going to solve for there? Y. So that means y equals 5x to the negative 2. Yeah? Okay, plug that in for the y right here. So cost is 20x squared plus 36x times 5x to the negative 2, which simplifies to be 20x squared plus 180x to the negative 1. So that's a lot of work to come up with that cost equation. No wonder those engineers make $80,000 a year right out of college. That's what you told me. Okay, so take the derivative. 40x. Okay, which I want to set equal to 0. So 40x equals 180 over x squared. Okay. So 40x cubed equals 180. X cubed equals, what, 4.5? Yeah. Alright, so for the first time we get a crazy decimal one. What's the cube root of 4.5? Maggie's on the case. You know how to do cube roots on there? You can go to the 1/3 power, but then you have to go through the parentheses 1/3. Also raise it to the 3rd power, then divide the answer by 3. Or you can go 3, and then if you go second and do the exponent button, then a root button will pop up. 1.65. Payson. Epic fail. Okay, and then what's 1.65 squared? Or whatever that answer is squared, don't round Yeah, until the end. Okay, and then go 5 divided by that answer. So we're trying to figure out what y is equal to. One more time. 2.725. There's what? 2.7225? How if we just call it 2.72? 5 divided by x squared.